So this is our presentation, which is an introduction to particle size analysis. Now we should think of the particle size analysis process as various steps that we should accomplish before we reach this end goal of even taking the measurement or presenting the results. And I split this to, on the left-hand side, we have sample-related steps prior to the measurement. And on the right, we might have instrument-related steps prior to the measurement. And these are things we should be thinking about and accomplishing before we just start the measurement. So we do need a sample, and where the sample comes from is very important. There are actually 2 or 3 sampling steps prior to the measurement. The first is we have to sample from the bulk. So in this particular slide, I'm showing what if we're measuring powders. On the right here, I'm showing a bulk powder sampler, which would remove a sample from a flowing process stream of powder. And on the left, I show thief samplers, which are used to remove a representative sample from, say, a drum of powder. The worst thing to do is just walk up to a drum of powder and scoop off the top. What we need to make sure is that the portion removed is representative of the whole. Now the portion that is removed from this bulk sampling is usually too large to introduce the entire amount into the instrument. So there's a second step of subsampling where we're going to reduce the portion taken from the bulk down to the portion that's going to be placed in the instrument. And I showed 2 methods here to perform this step. On the left, we have a spinning riffler, and on the right, a chute riffler. And both of these accomplish the task of taking the bulk sample and reducing it down to just the portion we want to measure. And it's important to do these properly because there's no point in taking the measurement unless the sample introduced into the instrument is representative of the whole. Now, let's say we have a powder and we're going to disperse it into a liquid. We have several sample preparation steps we may need to take prior to the measurement. We need to decide what solvent we're going to put the sample into. Is it into water? Is it into alcohol or some other solvent? And if the powder doesn't easily wet, we may need to add surfactant in order to wet the particles so that they'll go into dispersion. If the particles are agglomerated, this is an image of an ultrasonic probe in the beaker here, and we may need to add ultrasonic energy to disperse these particles so that we measure the individual particles rather than the agglomerates. As we switch to the right-hand side here, where we look at the instrument-oriented steps, what I wish happened more often, which doesn't always happen, is ask the question before you begin this, how are we going to use the data? What's important? And that may be important in helping us select which technique we're going to use. Prior to using the instrument, we should always make sure the instrument has been recently calibrated or verified. And how often we need to do this should be either a risk-based decision, how important are the results, or a question of the environment we're working in. Are there regulations that require us to perform verification, calibration regularly, or just the quality environment? Do you have your own ISO processes in place that require frequent verification? Now, if it's an unknown sample, we may start with very general settings on our instrument, or if we know the sample well, hopefully we can optimize this to the specific settings for this sample. Now we do the measurement. And when we take the measurement, we should be thinking about how long do we need to measure the sample, which could be related to how many particles are actually inspected and how many repeats. Down here in the interpretation step after we've finished the measurement, in general in particle size, we don't want to believe anything unless it is repeatable. So we'll check repeatability. Do the results make sense? Would it compare to other results I see from other methods? And after we've completed this, we can then generate the report. We can decide which of the numbers are important to highlight, such as a mean, median, or mode, which we will define in a few slides, and we can decide which kind of a distribution are important to show on the graph so that people can easily visually interpret these results. And don't forget about the chemist. Is the person operating the system? Are they well trained? And sometimes we might even question the motivation of the chemist. So all these things could be very important. In the end, we're going to generate a result. And as we generate the results, we need to create a particle size distribution. In order to do that, on the x-axis of a graph, we need to have some parameter describing the size of the particle. And particles aren't spheres, and it's almost impossible for one size to fit all for all kinds of shapes of particles. But if we look at this irregularly shaped particle, there are various ways where we can define a single number we can use to describe the size of the particle. If you look at the distance between parallel tangents, these are called the Fourier diameters. And the longest Fourier diameter would be the length, and the shortest one would be the width. There's also something called the Martin diameter, which is the mean chord length, or one that separates a particle into equal areas. But most frequently what we're going to include here is an equivalent spherical diameter, a diameter of this size is equal to the projected area or the volume of the particle. And most often in particle size, even if we're using image analysis where you get the shape information, on the x-axis we're generally showing the equivalent spherical diameter on the x-axis as we show the particle size distribution. We are always going to be showing particle size distributions. It's important to never focus on just a single number. This is about measuring the distribution. I'm showing some distributions here on the right. And first, let's talk about some of the modeling involved to do distributions. Some techniques, such as the active size and the counter techniques, create these results that are model independent. Model independent means every single particle is assigned a unique size, and as we build this distribution is directly related to the parameter that was inspected. Other distributions are model dependent. So for instance, if you're using dynamic light scattering, such as the NICOM system, we assume a Gaussian or normal distribution, which can be defined by two numbers, a center point, such as the mean, and then a measure of the breadth of the distribution, such as the standard deviation. As you look at the distributions here on the right, you see three of these all have the same central point, but have different widths. A Gaussian distribution is defined by a distribution where the entire distribution is within plus or minus 3 sigma 3 standard deviations from the central point. That is a model-dependent distribution, and with dynamic light scattering show either one or multiple Gaussian distributions. If we think about laser diffraction, there we could claim that it's model independent. We don't force it into a Gaussian distribution, but these distributions are highly smooth and dependent on the algorithm used. So those also would fall into the category, though, of a low-resolution technique. On the right-hand side, we see what we would call the frequency distribution or the population function. And then down here below, we show the cumulative distribution, which shows the percent under a given size. And how steep this is an indication of how broad is that distribution. So we can either show the frequency distribution, the cumulative distribution. Sometimes we also will show a histogram, and you can think of a histogram as we are building these bars, we decide on the channel width, and the frequency distribution is the distribution that passes through the center point of each of the bars of the histogram distribution. We also have to decide what is the basis of the distribution. Is it number versus volume? I'll discuss this in just a slide. And we're probably going to create several calculated values as well, which are typically the numbers used in the specifications for the product. So if we're going to use calculated values, the most frequent calculated values to describe distributions are the mean, median, and the mode. The mean is some kind of calculated average. There are various averages we could calculate. The median is the point where 50% of the particles are above the median and 50% are below the median. That's also called the D50. The mode is the highest point in the frequency distribution. And for a symmetric distribution, the mean, median, and mode will be all the same, but as you see here, for a non-symmetric distribution, these are different values. With dynamic light scattering, we have another value we look at, which is the intensity weighted mean. When we use laser diffraction, we might focus on 3 points. The D50, the central point, is the median, is most frequently used. But we could also define the D10, D50, and D90. 90% of the particles are below the D90, 50% are below the D50, and 10% are below the D10. If we're using a counting technique such as the AccuSizer, we can use either number or volume-weighted means, and we can also make these calculations of D10, D50, D90. So these calculated values are typically the ones we use for specifications, and would be the numbers of most interest in the final result. And I'm just going to point out only once in this talk, if I use a graph from any other place, I will give the reference here. There's a very good NIST reference publication, 960-1, which is available just on the internet, and that actually is a very good reference point for people who are new to particle size analysis. So as we look at distributions, we can decide whether or not to create it as a number or volume-based distribution. Let's understand the difference between the two. What if we have these three particles? They are 10, 20, and 30 microns. If we were to plot them on a number distribution, we have one each at 10, 20, and 30 microns. So we see an equal weighting at all those sizes. But now if we add up the total volume of all these particles, and then we proportion here in the volume distribution, what percent of the total comes from each of the three sizes, we see that over 70% of the total comes from the 30 micron particle. So volume distributions are always weighted to the larger size than number distributions. Calculating the average here seems very easy. It should be 20 microns, but that's using an arithmetic mean. And we could look at various size standard documents which will quantify how to calculate these various means, and I will give you these references on the second to the last slide today. The mean here based on number would be 20 microns, but the volume mean, which is also called the D43, is actually up at 27 microns. So how we calculate the results and how we graph them will make the results look very different when actually it's the same data just presented on different bases. So it's always important to understand what should be the basis of the distribution, the number or the volume distribution. I'm going to show some results here. This comes from our AccuSizer, which is a counter-based technology, and as you look at the right, this is above it's the number distribution and below it's the volume distribution. On the right is from a narrow symmetric distribution, and on the left from an asymmetric broad distribution. On the right, this is a polystyrene latex standard. And what you see is the mean, median, mode in the number and the volume basis are fairly similar, right? The mean is 13, the mean is about 15. And these look similar. But as you have an asymmetric, and in this case a multi-peak distribution, this is the number distribution above and the volume distribution below for a real-world sample. See how the volume distribution appears much larger? It's the same results just presented on a volumetric basis. And as you look at the number mean at 4.45 versus the volume mean at 20.45, you see how different these numbers become. So how are we going to choose volume versus number distribution? It comes back to that original question of how am I going to use the data? If this information is being fed to a chemical plant and you're a chemical engineer, you're used to doing mass balances. And mass and volume are equivalent if we have constant density. So if we're running a plant, we're probably interested in the volume distribution. On the other hand, if we're doing some kind of contamination work and we're trying to understand the contamination in the sample, there, if we're interested in particles per ml, then we're probably thinking on a number basis. Another way to think of it is we will do many measurements on the volume-based distribution, but if we're comparing results to another technique like a microscope inherently gives you a number distribution. So if we're going to compare to a microscope, then we might do this conversion from volume to number. But be aware, for non-symmetric distributions, this conversion from volume to number can get quite tricky. We're next going to talk about techniques. Hopefully we've understood how we're going to use the data, and now we're going to understand what technique are we going to use to take the measurement. The referee technique in our business is the microscope because it is the most direct measurement of particle size. We have some kind of graticule, some kind of a reticle, and as we look at the particle under the microscope, we can say, yes, that's 10 microns, that's 20 microns. What I'm showing here on the right is a scale of particle size on a log scale on the right. And these are various kinds of samples we'd be measuring, and I'm showing the dynamic range of some of these techniques. Dynamic light scattering is one of the best techniques for measuring submicron particles. But if we're trying to measure very large particles, maybe sea sand, then we're going to use sieves, which are good for measuring very large particles. A very popular technique for general particle sizing is laser diffraction. You'll see it has a very broad dynamic range. That's probably why it's fairly popular. Counting techniques have a higher resolution and give us a concentration. I show you here the dynamic range of the particle counters from particle sizing systems. But realize that as we use light scattering techniques, which are usually ensemble techniques, lower resolution and no concentration information is available. So as you look at other techniques, we can actually then understand what's the size range that they can work in. This is a busy slide, but I'm partly just giving this to you as references because there's so many sizing techniques. I could spend the next 35 minutes just trying to summarize these various techniques. They include acoustic attenuation, centrifugation, electrical sensing zone is when we start talking about counting, laser diffraction, microscopy. There are also techniques based on separating the particles, such as field flow fractionation. So I'm giving you here the physical principle. I'm giving you the basic concentration range you can work in and the basic size range. The graph down here I found from AGFA, where they're saying we have very many techniques in their laboratory, and they're talking about the dynamic range for these various techniques. So another point that's very important to understand is in a well-organized particle size lab, you have more than one technique. There should always be a microscope and hopefully more than one technique to cover a given size range. And as you can see here within some of these size ranges, there are certainly very many techniques that are available. This is a slide where we take a closer look at microscopy. This is the same scale here, but down here we show which kind of microscope can work within which size range. So for instance, if we're using classic white light microscopy, it's only good down to about a micron. And if we want to work below a micron, Then we're going to have to switch to scanning electron microscopy or transmission electron microscopy. Then we could generate results such as we see here. I think these are probably gold nanoparticles of some type. And we could say, yeah, that's 1 micron, that's 0.5 microns. But when we're using microscopes, some of the things we have to be careful with there is one is the number of particles you look at. And the broader the distribution, the more particles you need to look at to really be able to adequately define that distribution. And also, it's too easy to start counting what it is we thought we wanted to go find. So there could be some inherent bias if someone is doing this and they're trying to prove that these are all small, very well dispersed agglomerates. But the microscope is our referee technique and is usually what we would refer to when we start questioning results from other techniques, saying, does it make sense? If we're going to measure larger particles, then we might be using sieves, which are screens with known sizes. They're good for very large particles. This is a standard table of sieve sizes, and you'll see that it goes down to 20 microns, but personally I start questioning data below about 38 microns, the number 400 sieve. The resolution you get from sieves is really related to how many sieves do you stack one on top of each other. So you stack the sieves, you add the powder, and then you shake them, and you see the percentage on each sieve by weighing each one after you've agitated the powder. So this is a very good technique, been around a long time, great for powders. There's some variation due to the wear of the sieves. Blinding has to do with what size particle can really fit through a given opening, and also the operator experience, which is true for most of these techniques. For submicron particle sizing, the most popular technique is dynamic light scattering. The image I showed to the right is kind of showing the basis of Brownian motion. The particle is yellow here, and the black particles you see are the water molecules. And as the water molecules bang this particle, it just moves in a random walk. It diffuses through this liquid. Small particles would move much larger than large particles. The way we perform the measurement is a sample is placed here in a cuvette. We have a light source, and we look at the light scattering at some angle. I'm showing it here at 90 degrees, but for instance, a night comp could work at any angle we choose. So we look at this light scattering, then we're going to feed this into a device known as an autocorrelator, which we're going to use to count the photons as a function of time and look at that change of rate, which is then used to come up with this diffusion coefficient. Be careful, this is not diameter, this is the translational diffusion coefficient. So from the autocorrelation function, we can derive the diffusion coefficient, and then we use the Stokes-Einstein equation, where if we know the temperature and the viscosity, we can calculate the radius or the diameter of the particles and generate this result. So this is the basis of dynamic light scattering, probably the most popular tool for submicron particle size analysis. When we look at results from dynamic light scattering, the result we generate is an intensity distribution. This is the particle size distribution based on the intensity scattering of the particles. And we could convert that to volume or number, but the basic results and the ones we should typically stick with is the intensity distribution. And if we're going to use two numbers to describe the mean and the central point, if we look at the ISO standards for dynamic light scattering, it'll tell us we should use the intensity mean, which goes by several names, including X bar, DLS, and the Z average. And then to define the breadth of the distribution, we can use the polydispersity index. As you look down in the lower left, this is an intensity distribution. It's always larger than the volume or the number distribution. We should only really be converting this when we're trying to compare to other results such as an SEM or TEM result. Now, the data interpretation trick with dynamic light scattering is sometimes, was this result really a single peak or multiple peaks? And what's automated in the NICOMP DLS system is by looking at this, the calculation called this chi-square, then we'll automatically suggest to the operator, look, that was a very high chi-square value and we think there are two peaks, and split those two peaks. So in the NICOMP DLS, we actually automate this interpretation, which is probably one of the more difficult steps of using dynamic light scattering. One of the most common techniques in particle size is laser diffraction, which is an ensemble technique. Multiple particles are passing at the same time through this inspection zone, and out here we have multiple detectors at various angles. And what laser diffraction does is it looks at this light scattering, feeds it into an algorithm, and calculates the particle size distribution. There are various algorithms we could use, Fraunhofer or the more complete Me theory, which requires knowing the refractive index of the particles. And this is a quick, easy technique which has a broad dynamic range. It can be used on all kinds of samples like powder, suspensions, and sprays. And it generates beautiful results a lot of the time, and other times results that are much more difficult to interpret. And these results will vary by the vendor, the model, the refractive index. So a quick, easy tool, but again, some challenges in the data interpretation. And I'm going to show you a few graphs which helps describe this challenge in data interpretation using laser diffraction. On the far left, we see the same sample was analyzed on various laser diffraction systems. And you see 3 different results depending on the vendor that was used, because these algorithms are very dependent on the maker, because this is essentially their intellectual property. They're saying our algorithm is the best. In the middle graph, which came again from the NIST practice guideline, this is one sample, and then the differences are just in the refractive index assumptions. And what you'll see here is for this particular refractive index assumption, there are no particles under 1 micron. But then as we vary the absorption component of the refractive index, saying there are more and more submicron particles. And it can be very challenging when using laser diffraction to understand, is there really anything under 1 micron? And you can't reach for that microscope very easily to determine that. So this is one of the challenges to interpret results from laser diffraction. And then on the right, this is a single sample that was just run different ways on a laser diffraction analyzer, and look at how different these results are. All the way ranging from, is there anything up at 100 microns, or is there nothing over 2 microns? And it's just a question of how was the tool used, a single vendor, but just how do you use a tool can have a tremendous influence on the results that are generated, making it very challenging to perform the data interpretation. The next technique we're going to look at are particle counters. In the upper right, this is just a schematic of the Coulter principle, where the sample is suspended in an electrolytic solution, and as the particle passes through an orifice, there's a current drop. And one at a time, these particles are counted and sized, so this would be a high-resolution technique. In the lower right, this is the basic schematic of a light obscuration sensor. As a particle passes through a light source, it blocks some of the light. It creates a change in a pulse. That's fed to a pulse height analyzer, and that is converted into a particle size for each individual particle. And this is the basis of single particle optical sizing. So this is showing a sensor based on light obscuration alone. Now the LE400 sensor, which is the basis of many of our single particle optical sizing systems, actually has 2 detectors. Here is the light obscuration or extinction detector, which looks at the diminution of light as each particle passes through this ribbon of light. I give you the basic dimensions of the sensing zone right here. We constrict the flow, and then there's this narrow ribbon of light. But what we've also done is we've added a second detector, which is the scattering detector. So we take these 2 signals, the extinction and scattering detector, we adjust the gain, we feed it into a compression circuitry, and then we sum them, and this summed signal is then fed into the pulse height analyzer, which is the counter. And through the use of a calibration curve, we then assign for each particle the particle size and can build the particle size distribution at very high accuracy and very high resolution. There are 2 more advanced sensors that are built into the accusizers now. These are based on focusing the beam. The LE400 had a collimated beam. It was equal across the entire measurement zone. But if we want to increase the concentration range we work at, and also to be able to measure smaller particles, we need to focus this laser beam. In the focused extinction sensor, the FX sensor has a single detector, a focus beam, and that's going to look at the light obscuration and can measure down to 0.65 microns. If we want to measure to smaller size ranges, we now have the FX nanosensor, which can measure down to 150 nanometers or 0.15 microns, where we have 2 detectors again, the light obscuration detector and the light scattering detector. As we measure at smaller particle sizes, it's important to be able to measure at higher concentrations, because as you get to smaller sizes, there are more particles. So what's equally important with these sensors is the ability to measure at very high concentrations without having any coincidence error. The coincidence error being defined as having more than 1 particle at a time present in the measurement zone. So these are the more advanced single particle optical sizing sensors now built into the new Accusizer system. Some of the advantages of using counters, and specifically the Accusizer, is the ability to be sensitive to a small portion of very large particles. These are some experiments I ran recently. What you see in the upper right is this is a CMP slurry, which is a slurry used in the microelectronics industry. And what we did is we spiked the sample. We just took 3.4 microliters of a 1 micron polystyrene latex. And when we spiked 3.4 microliters into 250 mLs of the CMP slurry, we found the second spike. I then took the same sample to a laser diffraction analyzer, and before I ever found the second spike, I had to add 360 microliters into only 4.3 mLs of the CMP slurry. So in this particular experiment, which is very tightly controlled, we proved the accusizer was 600 times more sensitive to catch these tails in light scattering. And this gets back to my original point of light scattering, great general tool, but it's a low resolution technique, and you really need to look at counters to have this high accuracy and sensitivity to the presence of a few large particles, which are often detrimental to the quality of a product. Now, if we start comparing different results, these results will vary sometimes depending on the effect of shape. This is a study I found where 3 samples were taken. This happens to be glass beads, crushed glass, and mica. And it was run on 3 techniques: a Coulter counter, a laser diffraction analyzer, and a technique based on sedimentation. And for the glass beads, you'll see the 3 results are fairly similar. But then the crushed glass, which is more irregular, you'll start seeing some deviations. And as you look at mica, which has a much higher aspect ratio, then you start seeing great deviations in the different techniques. So just be careful when comparing different techniques. One point is, if you have different shapes, that's going to accentuate these differences. Not every sample in the world is a nice narrow distribution of glass beads, and that's when we start seeing larger differences when we compare these different techniques. Here's a result which was published in American Pharmaceutical Review a few years ago, and this title was the role of particle size analysis in developing nano-sized drug products. And this actually is a pretty impressive result. So they were apparently very careful. This is the SEM micrograph of the sample, and it looks like there's 2 different sizes. And for both laser diffraction and dynamic light scattering, you see a Z average of around 300 nanometers and a D50 of around 300 nanometers. So sometimes these results can compare fairly well, but never expect the same answer when comparing these various techniques. But this is just saying sometimes it can work out, but it usually doesn't. On the right, another example from the NIST guidebook. Here we see this is actually, again, glass beads, which are fairly spherical and not that broad of a distribution. And it's comparing results from SEM, from a sieve, and a laser diffraction analyzer. And for the smaller sizes, fairly equal, but then as you get to the larger sizes, you see the deviation from the laser diffraction results. And that's not unusual because laser diffraction results always broaden the distribution, more so at the large size range. So this is more what we always expect when we compare laser diffraction to other techniques, is this broadening, in particular at the larger size ranges. So that's not that unusual. One of the other very important steps we have to be aware of if we're ever going to compare results or be able to interpret results is the sample preparation step. And what I'm going to do here is show you 3 results where the sample prep played a major influence on the results. The upper right one is where we look at the choice of solvent. So this is the same sample dispersed in 3 kinds of alcohol. A is ethanol, B is IPA, and C is methanol. And what you see is a completely different result when measured in methanol. If you just see results and someone says, I measured it in alcohol, that alone isn't enough information to really understand how was that sample prepared in order to be able to ever compare the results or be able to reproduce the same results. The next 2 results I show you are the effects of ultrasound. So I showed you in the beginning slide using an ultrasonic probe to disperse the particles. In the sample here in the middle, this is a result, I think it's from a silica. What happens here is, but without ultrasound, we have a median up here at about 200 microns. Then after we use an ultrasonic probe, we see smaller particles and still larger particles here. I would look at this result and say, you know what, maybe if we hit this with more ultrasonic power, maybe these are the individual particles and these are still aggregates. So you can't just say I use ultrasound. It's a question of what energy level and for how long in order to make these results ever be reproducible or comparable. And the result you see on the bottom is taking a sample, and this is D10, D50, D90, and without ultrasound we have some larger particles. The measured size is up here at 10 microns. But then as we add 1, 2, 3 minutes, we see how much ultrasound we need to apply in order to get stable results. And this is what we should be looking at when we do method development. If we're going to use ultrasound, at what power and for how long, and make sure that we add enough power to have stable results. And that's a very important process to be very careful with when you're doing method development for any of these techniques. Now I'm going to show a case study where I helped a customer. This particular customer actually bought two instruments from particle sizing systems. They bought a NICOMP and the Accisizer because they wanted general particle sizing techniques to cover a broad dynamic range. Now the Accisizer, the image you see here, was bought for just a general purpose particle size analyzer. And the first sample they gave us was actually a powder. And they gave us the results of a laser diffraction analyzer. This is what you see here in this column. They say, all right, this is a powder we need to measure, and these are the results from the laser diffraction analyzer. Without knowing whose diffraction analyzer was it, how did they do the sample prep, did they use ultrasound, all we were given was a certificate. And when we first used the Accisizer, we got results that were about 3 times larger. And the customer was despaired, saying, why doesn't your result match? Well, let's take a look at the sample preparation we're going to use here. And we spent a day creating a good method. And that included using first a surfactant. It was EGPAL 630 actually, which is a good non-ionic surfactant. We took a known amount of powder into a beaker. We dropped a low concentration surfactant solution on top of the powder. We then filled that up with a known volume, used an ultrasonic probe, and looked at the effect of ultrasound on the results. And after about a day's work where we got the dispersion proper, this is a result then using this particular method, and here are the results from the Accisizer. And what you see is the D90, we had 15, they had 18, 9 versus it was supposed to be under 8.5. So fairly close results, and this is kind of the real world. When you create a good method and you're comparing different techniques, in particular if you don't know how the sample was prepared, very often you just get the result saying this is the size we got. Yeah, but how did you prepare it? So this is doing the work to try to get the results comparable, but this is a great day. Don't think that these are going to compare within a half a micron without having much more information of how that sample was prepared. I'm going to give you some useful references, I hope so now. I've actually spent a fair amount of time on various ISO standard committees, and this is just like the first 8 of about 35 standards you can get from the ISO website. They're not free, you do have to buy them. But that includes just graphical representation of distributions, the calculation of different averages. So I'd said before, if you want to really look into detail the calculations used for those various mean diameters, certainly this ISO standard would show how those calculations are made. And it can show general calculations, then also terminology and techniques. Now, here in the US, the American Society of Test ASTM and also ANSI will give you some standards which are ASTM based. Now, the ASTM standards are usually for a given industry. There could be an ASTM standard for measuring cement and an ASTM standard for measuring powdered metals. And these methods are usually round-robin based, meaning that industry and instrument experts get together. They run a round-robin. They say, let's run the sample the same way in multiple laboratories, how close to the results. And then they'll publish a test saying if you want to measure cement using Sieves, this is how I suggest you do it. The NIST guidebook, which you see right here, is a very useful guidebook available for download on the NIST website. Gives a lot of great information. And as you look at books that have been published on the topic, Terry Allen's is a classic. It's been out quite a while now, and there's 2 volumes, a basic, and then volume 2 is about surface area and pore size. Henk Merkus, who came from TU Delft, actually wrote a great book a few years ago, very heavy on a lot of technical details on laser diffraction. And as I was preparing for this presentation, I actually found a new book which was edited by Sieves. And I haven't looked at this yet, but that's the point with technology. You should always be looking at the newer references as well. And if you really need additional information on understanding some of these basic concepts, here are some useful references that perhaps could help you. So that concludes today's talk, and I remember a Star Trek episode where Scotty yelled at someone for saying, how many times do I have to tell you the right tool for the right job? And that's true in particle size as well. Understand how you're going to use that data. Make sure you're using a technique which is appropriate for how that data is going to be used. Hopefully you can choose a technique and you're not locked into just what is in the lab. Be very careful when you're going to take that sample and come up with the sample preparation steps. Take your time. Investigate each step, such as sampling, dispersion, interpretation, because all these are going to have a great influence on your result and for anyone else to be able to repeat the results that you're creating the method for. If you run into any difficulties on these steps, certainly we're always here to help you, both Bruce, myself, and everyone at PSS. And if you go to our website to the Documentation Download Center, here you'll see many application notes and also technical notes covering both basic fundamentals and techniques for particle size.